Okay. All right. So this transfer function here, I've got R and C in series of each other, and I basically use the voltage divider. V out is that whole thing, and I wrote the transfer function here. So the transfer function is this guy 1 over SRC plus 1. All right. That's my H of S. And basically, what we say is that this, if I have a sinusoidal input in general, we talk about the steady state of this, then H of S, we plug in for S equal to J omega. All right. So this guy becomes for me 1 over J omega RC plus 1. All right. So I plug in those particular values. So what I can say is, all right, I want to see what's the magnitude of this thing going to do as a function of frequency. So what's the magnitude going to do? If I plug in omega equal to 0 for this thing, what do I get for the magnitude? 1, right? Because I can get 1 over 1. That tells me that if my input was a DC value, omega equals 0 is DC. If I put in a DC value at my input, I get the same DC value at my output, right? No current flows, the capacitor is an open, V out and V in are equal to each other, okay? What about as the frequency increases? So in this case, if I say in general, H of J omega is equal to 1 over J omega RC plus 1. If omega goes to a high number, so omega starts to approach infinity, what's the magnitude of that thing going to do? Without me, so first of all, I'm doing magnitude, so I'm kind of cheating, right? I should figure out what is the magnitude of that thing. What is the magnitude of that thing? It'll be 1 over the magnitude of the bottom. Okay? I don't want to do that. I just want to cheat and look at this and just say, what's going to happen to the H of J omega if omega goes to infinity? It's going to tend towards 0, right? So it tells me as omega goes to infinity, H of J omega's magnitude is going to tend towards 0. So what does that tell me? So what I just said here is I said at DC, which is the lowest frequency I can get, by the way, right? Because I can't get any lower than 0. At the lowest frequency I can have V out and V in equal to each other, all right? As frequency gets higher, the magnitude of this thing tends towards 0. So if, first of all, we talked about this in the previous class, right? V out equals, if V in has that shape, V in cosine omega t, what's the value of V out always in general? What's the amplitude of the input times what? Let's talk specifically about the amplitude. What's the amplitude going to be? It's going to be the amplitude of the input times what? Yeah, you got it. Yeah, so basically the magnitude of V out is always the magnitude of V in times the magnitude of the transfer function. Basically, if I just talking about amplitudes, that results right, and you got it. If I put the whole time domain thing in there, that's right. So tell me what that tells me about the amplitude of V out as omega gets to be a really high big number. In other words, as the frequency gets higher, what's true about the amplitude of the output? Right? It's going to get smaller, and in fact, it's going to get really, really small, right? It's going to get like it's gone, right? It's going to tend towards 0. So I'm saying that a low frequency signal for a low frequency signal, output and input are really close to each other in terms of their size. For a high frequency signal, it's saying it actually gets made much, much smaller. The term I'm going to use for that is that it's attenuated. All right, it's made smaller. All right, so in general, what we do with this thing is, all right, I want to think through this guy a little bit. What I have for it is I took an example. I took a resistor that was 1.59 kilo ohms, which you wouldn't, first of all, unless you really needed to, nobody would ever get a 1.59 kilo ohm resistor, right? What would I get? Any ideas? Boxman, do you have any ideas? I would get a 1.6 because that's a standard value. There's a set of standard values, right? And so I would find that that's a 1.6 is the closest standard one. All right, in other words, if they tell you like 1.5967, you could put a bunch of stuff in series and parallel to make that. Typically, we just get it close. All right, when we build it that way. Anyway, neither here nor there. If I take those two things together, R times C, that works out to be, in this particular case, I think, I wrote it down and didn't bring it with me, which is going to be problematic for me later, I think that's about 629, I think. I think this works out to be about, sorry, 1 over RC, at least, works out to be about 629. That's why I chose those values. All right. So why did I look at the 1 over RC value for them? We talked at the very end last time about this idea of poles and zeros. Did I start recording this? I did, didn't I? Yeah, I did. All right. I talked about poles and zeros. This guy has a what? You guys remember from a short while ago? Already go out the brain. That's fair. What does zero do? A zero is a simple one to remember. What's a zero do? A zero is the value of S that makes the transfer function zero, right? A pole is a value of S that makes the transfer function infinite. Is there a value of S that's going to make this guy equal to zero? No. But there is a value of S that's going to make it infinite. What would that be? If S was equal to what? If S was equal to -1 over RC, if I plug that in there, right? What would that? So if S was -1 over RC, I would have -1 over RC times RC. What's that? -1. -1 plus 1 is 0. Right? So that would make this guy infinite. So we've got a pole at -1 over RC or -629. All right. That has units of radians per second. All right, because why do I know it's got units of radians per second? Well, S is equal to j omega. All right, but I'm not going to focus too much on that. What I just said is this guy's got a pole. That's all I'm going to worry about for right now. All right. What I want to do is the transfer function is a function. We've already said for this guy, no matter what value of RC that I'm using, we said that basically if I put a DC input into this thing, the output would be at DC would be exactly equal to the input. If I put in a high frequency, as the frequency got higher and higher, the magnitude of the transfer function would drop to 0. So what that's telling me is the magnitude has somehow got to be a function of frequency, right? So, all right, so now I want to generalize this for a second. Let's say I have a sinusoidal input, in which case I talk about not h of s, but h of j omega. And I get this whole thing. J omega RC plus 1. What is the magnitude of this guy? I take the magnitude of this. Well, yeah, so it's the magnitude of the top divided by the magnitude of the bottom. Just take it real slow. All right. What's the magnitude of 1? Well, it's just 1. What's the magnitude of the bottom? How would I write that? Square root of real part squared plus imaginary part squared. What's the real part? The real part's 1, right? And the imaginary part's just the omega RC, right? So it's omega squared R squared C squared. Okay. And if I plotted that, it looks like this. Now, what did I do? I plotted this versus frequency. And this plot's pretty consistent with what we did. We said, okay, if omega is equal to 0, the magnitude of the transfer function is 1. Okay, well, that's exactly what it is. All right. And then what I have is as the frequency gets higher and higher, I see that the magnitude's tending towards 0. This is the way we look at this thing. Because what we say is the usefulness of this thing is to say, all right, if I have an input that has a frequency in a particular range, what's the magnitude going to be? All right. And I like to use this thing as a design tool. We're going to look at some examples of how I do this. So how would I use it? Right. So basically, what I'd say is I'd look at sine waves at a particular frequency, and I'd try to figure out how big are they going to be using this graph. Okay. So let's say I have an input voltage 5 volts. What's the output voltage going to be? Well, it's going to be 5 times the magnitude at that frequency, which is what? 1. The output's going to be 5, right? Where we're basically saying this is V in times the magnitude of h of j0. And I could also say that's times the cosine of 0t, right? Because I know that what's cosine of 0t always equal to 1, right? So that's a sine wave. It's just a sine wave that doesn't change, right? It just stays flat. What about if I had this guy here? I got 2 different inputs, I guess, that I considered. V in is 5 cosine 629t. Well, here's what I do is I go, so what I know is that V out is always equal to whatever the amplitude of the input is times the magnitude of the transfer function at the frequency. So what frequency am I looking at here? If I have 629t, what's the frequency of that 629t? What's the frequency of cosine 629t? 629. Yeah, 629. Right. So I'd say h of j 629, right, times the cosine of 629t. And then what do I say about the angle there? Transfer function, yep. At 629. Out of space to write that. Okay. So let me clean that up. Messy looking. Plus the angle of h of j 629. Like that. Okay. So what do I have here on that graph? I have the magnitude of it. So what does that tell me the magnitude is at 629? So what I have there, that is something in MATLAB where I use the cursor to let it tell me the value at a particular point. So it tells me at the x-axis point, 629, I have a y-axis value of 0.7071. So what does that tell me this guy is equal to here? What's the amplitude? 0.7 times that. So it's basically 5 times 0.7071 times the cosine of what? 629t plus whatever that angle is. Now, I didn't graph the angle, but the angle would have a graph too. If I looked at what that angle was, I'd find out that it's negative 45 degrees. Okay. All right. But in general, I'm only going to worry about what's going to happen for the amplitudes here. All right. So, all right. So V in is 5 cosine 2000t. I want to figure out for this guy, what's the amplitude of the output going to be? So I want to know what's the amplitude. So what's the magnitude of V out going to be if I had 5 cosine 2000t? What would it be? How would I approach this guy? What's that? Let MATLAB do it. Okay, well, I'm old man. I'm going to look at this thing and say, how do I approach this thing? I've got a graph, right? How do I use it? Yeah, figure out what the y-axis value is when the x-axis value is 2000, right? So at 2000, I don't know, it's about there. Yeah, MATLAB get it more exact for me for sure. And that's what I would really do, but we're learning, right? So what I would say is that this would be 5 times the magnitude of HJ 2000, which we just determined was, I don't know, to me, it looks like it's at about 0.3. So I would say this is about 5 times 0.3. So what that tells me is if I were to go on the oscilloscope and put the probe across that capacitor, I would see a voltage whose amplitude was 5 times 0.3. So it'd be a lot smaller than whatever the 5-volt input is. Okay, you guys follow that? And there'd be a phase shift in that cosine and everything. I don't worry in this class about the cosine stuff, or sorry, about the phase angle stuff. Right? There will be a phase angle. We're not going to worry about it. It's just more stuff for you guys to stick in your head. If you take controls, we in control systems, you think a lot about that phase angle because that deals with the stability of systems and things like that. Okay, which we're not going to talk about that here. All right. The important thing for you guys is going to be that you can use this transfer function to figure out what's going to happen to amplitudes. All right, as I go through this. All right, questions about that? All right. This leads to, I want to understand like what's going on in this particular circuit, right? So if I think about it, what I have is in this circuit, I have a voltage divider, right? D sub C of T. If I think about what's going on in the circuit, the capacitor has an impedance, 1 over j omega C. If I think of the impedance of that capacitor as a function of frequency, right? So Z sub C is 1 over j omega C. The magnitude of that is what? What's the magnitude of 1 over j omega C? 1 over the square root of omega C squared. So it's 1 over omega C, right? As omega gets to be a bigger and bigger number, what's true about that guy? It tends towards 0. And when omega is equal to 0, it tends to infinity. So what that tells me is that DC, what is the capacitor? It's an open, right? At DC, the capacitor is an open. At infinite frequency, the capacitor is what? Short. All right. So that's entirely consistent because you're saying now at DC, how much current flows in this thing? None. At a really high frequency, how much current flows in this thing? Well, it's set by whatever the resistor is, right? If the capacitor became a short, what would that do? What would that tell me? At a high frequency, basically it's saying I have this circuit. So what's the voltage have to be across that capacitor if it's short? 0, right? So the behavior that we're witnessing here, basically, which we can be represented by this function that I plotted, is you can think of it in its two extremes fairly easily, right? At low frequencies, it's an open. High frequencies, it's a short. Entirely consistent with what this graph is doing. This behavior, this guy right here, this is why I call this a low-pass filter, all right? So I call this a low-pass filter because we're going to define some terms here, right? What I'm saying is this particular circuit passes certain frequencies and attenuates others, right? So the passing means it just passes them right through. So if I have a low-frequency input, that low-frequency input just passes right through to the output without any being affected. If it's attenuated, it means that the signal decreases in its amplitude. In other words, it's made smaller, right? So this guy says for low frequencies, so somewhere down here, right? The signals that I apply to this thing, voltages that I apply to this thing, pass through. For high frequencies, they're made smaller or attenuated. So I call this guy a low-pass filter, because what he does is he passes low frequencies and he gets rid of high frequencies. Now the question is, what is the meaning of high and what's the meaning of low? Because I can build two different circuits, and what's high to one circuit and what's high to another circuit could be different. That's where the idea of the pole comes in, because the pole is going to change that pole. Okay, and that's why I defined what that thing is. All right, we're going to talk about that in a minute. Important thing is I want to get this idea across, right? This is a low-pass filter. Passes low frequencies and attenuates high frequencies. In general, we kind of define sort of the family of filters here, right? So here's the family, and there's maybe one other one that I would put into this one, but these are kind of the main ones. Low pass filter, high pass filter, and band pass filter. And the way that we sometimes draw these things here is I drew the magnitudes of these things versus frequency. All right, so I define here this value omega C. What I call this here is sometimes it's got different names, but I use the C because I call it the cutoff frequency. All right, so it's the frequency of, if I had an input that was greater than omega C, it would be quote unquote cut off, right? It would not pass through this thing. So it's the cutoff frequency because we say anything above that frequency is cut off. High pass filter is the opposite of that. And a band pass filter is one that passes everything within a particular band and gets rid of everything else. The other thing sometimes that exists, we talk about a band stop filter. What do you think that would do? stops a certain band. All right, those are probably less common. All right, low pass filters we have all the time. High pass filters we have all the time. Once you understand those concepts, it changes your world a little bit, right? It did for me, right? So right now, your eyes are all low pass filtering, right? So those lights up there are changing their frequency probably 10,000 times a second, but you don't see that, right? The reason you don't see it is because your eyes are low pass filtering that behavior. All right. This is a really important phenomenon that we use all the time, all right, in nature, this idea of low passing something. Now, the thing about what I have right here, these are ideal pictures. Like ideally, what I'd like to do is I'd like to design a filter that passes everything below a certain frequency and then lets nothing else out after that. Nature said, no, that doesn't happen, right? What we have in reality is something like this, all right? Is it rolls off more gently. Those pictures that I have there on the left, sometimes we call these guys brick wall filters because they look like a brick wall. They're very steep, right? They just go straight up. Those don't happen for reasons that I beyond what I want to talk about, but nature doesn't allow that to happen. What they generally have is they fall off a lot more gently, and they look something like this. Now, what happens if you did, and there's reasons, we're going to see this in a second, right? Let's say I want it to fall off faster. In other words, that magnitude is falling. And I'm saying, let's say I want that magnitude to decrease faster. In other words, instead of looking like this, let's say I want it to look like that, right? How would I make it do that? Any ideas? Well, potentially. The idea that you would go to is you would actually do what I call a second order filter. All right. I called this guy a first order filter. Why did I call this guy? So this is first order. Why is this first order and this one second order? What makes one second and what makes one first? Yeah, I got two energy storage components in this one, so it's second order. It would have a second order differential equation. It's a second order filter. All right. If I look at this, what I did is I tried to plot what their magnitude looks like. The one falls off faster. What we say is a first order system is going to have one pole. A second order system is going to have two poles. All right, we're going to show that more, but I defined the idea of poles. Poles relate directly to the differential equation, all that stuff. All right. Those can be designed to have the same cutoff frequency, but one rolls off faster than the other one. All right. Now, in looking at those pictures right there, the thing that I see with this particular, the first order and the second order, looking at those two pictures, that picture there on the right is kind of hard to even look at, right? Because basically the blue line that I drew is basically hugging the y-axis here and hugging the x-axis here. It's pretty hard to look at. And so we often don't look at it like that. How can I zoom in a graph like that? If I want to see the full graph, but I want to zoom in, any tools that I could use to do that? Well, yeah, yeah, you could zoom it with MATLAB with the magnifying glass, right? But if I wanted to try to draw the whole thing out, see it, let's say I want to see it over the same range of frequencies, but I want to really see it. There is a tool to do that. And that tool is, we're going to come back to in a second. All right, so what I want to talk about for a second is where would I use this thing? All right. So now look at this example right here. All right. So I've used this before. I talked about this when I was introducing the idea of AC and DC, but let's say I've got a PV array. So I've got basically a photovoltaic panel or a string of panels. Typically, if I have PV, I have a string of panels in a series, and then I stack them into the input of what I call, what did I call that thing? You guys remember that goes from DC to AC? It's an inverter, right? What it does is it takes DC and it converts it to AC. And the AC that it makes is this guy right here, which if I look at that, this guy has basically two different frequencies in it. I can't really see this that well, but there's a whole bunch of square wave action going on inside that fuzz, all right? So it's kind of like there's two square waves kind of coming together. And then ultimately what I want to do is I want to pass that yellow waveform through what I call a filter and make sure that the output looks like that green waveform. Right, that's the idea. Is I got this signal here that's got a whole bunch of crap added together, and I want to get rid of the crap and just have the nice, pretty sine wave come out of it. Okay, so that's the basic idea. So if I look at this, all right, I'll look at it from this perspective. So what I'm doing here is I'm showing I've got a current I sub L right here. This is the output of that thing. So this is the inverter is this box right here. That gets hooked up to this filter. So the filter is basically those two inductors that are right there. And what I've identified here is I sub L is the current going in, and then I sub G is the current going out. All right, that would be the total current. Now, this is what that current probably looks like, something like that picture right there, the bottom picture. All right, so this is what I sub L looks like here. And, it looks something like this, approximately like this. Basically, what I'm saying is I sub L is this 2 pi or 2 cosine 2 pi 60 t. So what's the frequency of that in hertz? 2 pi 60 t. What's the frequency in hertz? 60 hertz. All right, 60 hertz. All right. And so what I want is to get rid of the noise. And I drew in here, this is what the noise looks like. The noise basically has got this component at 100 kilohertz. All right, if I zoomed in on this, what I'd see is I got a 100 kilohertz term and I have a 60 hertz term. And what I want to do is, if I draw through here, I'd like to pass, this is the 60 hertz. The red here, this is the 2 pi, sorry. This guy is the 2 cosine 2 pi 60 t. So I basically have this term plus all this other stuff. What do you think I want to do? When I get to the grid, that I sub G, the outputs, in this case, my input is I sub L. My input is this. I want my output to be the red. Right? So what do I want to do? I want to get rid of that fuzz. Right? That fuzz is a high frequency. Right? How do I know it's a high frequency? How do I know that fuzz is a high frequency? Just look at the picture. How do I know it's a high frequency? Yeah, it's varying a lot faster than the sine wave is, right? So it's a much higher frequency. What kind of filter do I want if I want to get rid of that? A low pass. I want to pass the low frequency and I want to get rid of the high frequency. All right. So the way that I look at a problem like this is I say, all right, I usually have a design goal in mind. Now, I'm not going to be asking you guys to design stuff, but I want to sort of, why do I think of anything like this, right? So in this case, my filter has I sub L going in, I sub G coming out. So what I would say is, in terms of this transfer function thinking, this guy has a filter transfer function H of S. And I'm saying that I sub G would equal whatever the transfer function H of S is times whatever IL of S is, okay? And so if I use this approach, what I'm trying to say is I want to tailor the magnitude of H of S in the different frequency ranges. So what I've said here is that at low frequencies, in this case, 60 hertz, I want the magnitude to be 1. Ideally, at 10 to the 5th, right, 100 kilohertz. If I wanted to get rid of that 100 kilohertz, what do I want the magnitude to be at 100 kilohertz? What do I want the magnitude to be at 100? 100 kilohertz is basically the frequency of the high frequency noise here. Ideally, if I wanted to get rid of that stuff completely, if I wanted that, I want it to be 0. Right? I'd want it to be 0. Now, I can't make it 0. All right. I can make it really small. So what I say here is let's make it less than 0.01. Think about that for a second. If I had a 1 amp current, a 1 amp current would get multiplied by 0.01. What would its amplitude be? 0.01. So it'd be 10 milliamps. All right. So I'm taking something that's 1 amp. Right. If I zoomed in on the picture of this guy, he has a 1 amp amplitude. If I multiply it by 0.01, I turn it into 10 milliamps. So I make it a lot smaller. Okay. I make it a lot smaller. So this is the way that I would define that. So, all right, here's my filter. I want to figure out the transfer function from IL to IB. So I want you guys to help me figure out the transfer function there. How would I do that? So I know the current I sub L going in. I want to figure out I sub G coming out. How do I approach that? I could do KCL. All right. Now, first of all, if I sub L, let's think of it this way. Let's say I know that I've got a current source I sub L here. All right. Technically, with this, I use superposition. I get rid of that V grid, right? What would V grid be? Well, that would be the grid. That would be whatever the grid has. Okay. So this guy would basically be, if I did superposition, I have IL here. I have this inductor L1. And then I would have IG here, or sorry, L2 here. And the current here is, I'm going to say IG of S. If I do this in that phasor domain, Laplace domain, this is IL of S. And that would be IG of S. So if I know what the current is there, how would I approach this to figure out IG? What's it? Yeah, current divider, right? So I'd say IG of S is what? You got a current divider on problem 5 on the homework. Well, yeah. So he's got it. If I don't remember the relationship, I would say it's the voltage divided by what impedance? All right. What's the okay? Let's do it slow. What's the voltage? All right. Here's V. How do I figure out V? IL of S times the impedance, right? What's the impedance? 1 over SC in parallel with SL2, right? So that would be what? 1 over SC times SL2 over 1 over SC plus SL2 times IL of S, right? That's the voltage across that thing. Now, like we were saying earlier, what do I need to do to this thing? He's not in my general form, right? How do I get him to my general form? What do I got to do? Multiply by SC over SC. Right? When I multiply top by SC, what do I get? Those guys knock out. Right? And if I do it on the bottom, the SC's knock out in the first term, and then I get an S squared term on the second term. So this guy becomes SL2 over 1 plus S squared L2C times IL of S, like that. Okay. All right. Have I gotten my transfer function yet? No, I figured out what the voltage was. What was I trying to find? The current in that L2, that IG, right? So basically IG of S. How do I get IG of S from the voltage I just figured out? Divide by that impedance, right? So divide by, what is the impedance there in that branch? SL2, right? So I would divide that. What I would end up with is 1 over 1 plus S squared L2C times IL of S. That's my transfer function. All right. Now, stopping for a second. How many poles and how many zeros did you think of? Poles were what? Poles were the things that made the denominator 0 and made this thing go to infinity. How many poles does it have? 2. Okay. And no 0. So if I graphed this thing, what I would do is I would say, all right, let S equal j omega, and then plot the magnitude of this thing. All right. So if I did that, this is what it would look like. All right. So what's going on here? What's going on? So, and I did this just so we're clear. I did this for these values. L2 is 100 microhenries and C is 10 microfarads. Those are pretty normal values. So I got this. All right. Here's what the magnitude of H of J omega looks like. So what I see here is that apparently the magnitude of H of J omega is really, really big at some frequency. All right. What frequency would that be? Just out of curiosity, looking at this picture. Looking at this transfer function, any idea where it would be really big? And omega equal 1 over square root of L2C, it would be really big. Right? Whether you see that or not, don't worry about it. But at that frequency, it would be really big. When I look at this, though, this graph is pretty useless to look at. Right? And so, and I need this graph. Here's the 10 to the 5th. That's the guy I'm trying to make smaller. Right? Looking at this graph, how big does it look like it is at 2 pi times 10 to the 5th? It looks like it's 0, but the thing that's goofy is the magnitude here is 8 times 10 to the 4th, right? I don't know how big it is down there. So how can I fix this problem? Make a giant graph. What? Well, I don't know. I mean, what I'm looking at is the magnitude of this. I just want to look at the graph better. How can I zoom in on a graph better? Well, let's go back to something we know. Let's go back to logarithms, right? It's a big day today. We're covering a lot of stuff here. So it's logarithms. So X is all those different values, 10,000, 1,000, 100, 10, 1, 0.1, 0.01, and 0.001. What's the log of those things? Let's start with 10,000. What's the log base 10 of 10,000? What'd you say? 3? All right, so every time I think of Yahoo, just crying something, right? He's yeah, but he cry. He's very sad when this is happening. If I get 10 to the 4th, if I take the log base 10 of 10 to the 4th, what is the log? What is the logarithm? Something about exponents, baby. All right, that's the phrase of the day. All right, so what is it? It undoes the right. So if I take the log base 10, right? Log base 10 of 10 to the 4th is what? 4, right? What happens if I took the log? If I take the log of 10 to the something power, the power always comes down in front. So I always say this is 4 times log base 10 of 10. The log of 10 is what? 1. Yeah. So you're saying there's a chance, right? There we go. All right, so it's the log. All right. The log of 10 to the 4th is 4, right? If I took the log of 10 to the 3rd, what is that? No. Right? The log of 10,000 is 4. Right? The log of 10 to the 4th is 4. If I take the log of 1, let's keep going, right? If I did it for 1,000, what do I get? 3, right? What do I get for 100? 2. 1. What happens if it's 1? 0, right? Because it's 10 to the 0 is 1, right? What do I get for 0.1? -1, -2, -3. So what have I done? Let's just take. I went through a really big range of numbers in theory, right? I went from 0.001 to 10,000. That's a big range, right? And what did I do? If I go to the log of those numbers, on the regular scale of life, right? What we call the linear scale, going from 10,000 to 0.001. What have I done by taking the log of those numbers? Made them smaller. Well, I don't know. I guess in the case, I made them bigger. I made them bigger down there.
I just looking at the magnitude.
No, just what happens if I take 10,000 numbers ranging from 0.001 to 10,000. If I take the log of those numbers, what have I done? I've basically changed, I've compressed them in a different way, right? So what I do is instead of making this graph here where I plot everything versus omega, I'm going to plot everything versus the log of omega. And that's going to make that spread of numbers completely change. All right. So when I do that, I get this. Those are the same graph. Right there. The graph on the left is on what I call a linear scale. The graph on the right is what I call a logarithmic scale. All right. What I've done here is, so notice 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth are the same distance away from each other. Right? Because their logarithms are the same distance away from each other, right? So it's a log, that's what we call a logarithmic scale, right? So basically it allows us to separate numbers that are really widely separated from each other and make them on a, we have a term for this. This range from 1,000 to 10,000, this range here we call a decade. All right, so a decade can be, you know, a decade in a century, right? It could be the 1990s, or it can be a decade is the distance between powers of 10, like that. All right, so 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth. The other thing I do is I put the magnitude, so the y-axis value, I also take the log of it. And for reasons that I don't really want to kind of get into here, we typically multiply that by 20. All right, I don't want to get into the reasons behind that. Let's just say that we do. All right. And when I look at this, I give this at 20 log of some number, 20 log of any number, we give it a unit. It's a unit you've heard before. What unit is that? That's a decibel. Yeah, a decibel, all right, is what that is. And you probably heard before about like sound values are measured in decibels, right? So we call it, and so the sound scale is logarithmic, right? That's where the decibel thing kind of comes in. But 100 decibels is a lot louder than 1 decibel, right? Because it's a logarithmic scale. So we draw it like that because that graph on the left, it's hard to really tell anything. But if I draw it on a logarithmic scale, I can see much better what's going on. And when I look at this, now what was I trying to do? Well, I was trying to say that I wanted the magnitude at 2 pi 10 to the fifth to be less than 0.01. And I wanted the magnitude at 2 pi 60 to be equal to 1. All right, so where is that here on this graph? Well, 2 pi times 100,000, where's 2 pi times 100,000? Where should it be, roughly? Where's 2 pi times 100,000? What is 2? Give me a number for 2 pi times 100,000. 2 pi. It's about 628,000. Yeah, so where is 628,000? Well, it turns out there's 10 to the fifth. This would be 2 times 10 to the fifth, 3 times 10 to the fifth, 4, 5, 6. It'll be somewhere around here. Okay. So if I go and look at this carefully, I went into MATLAB and I said I read off the values of this thing. So we're just playing with logarithms here right now. What I did was I said at this frequency, 2 pi times 10 to the fifth, I got this value, 629 times 10 to the third. Okay. So I went to the graph and I read off that the value there was negative 51.9 decibels, with a decibel defined as 20 log times the number. I meant to get rid of that. I didn't want you to see that. All right. If I have 20 log base 10 of a number x is equal to negative 51.9. Help me out. How do I solve for x? That 20 times the log of something is equal to something. What do I do? What would be step 1 in trying to solve for that x? So divide by 20 first, right? So log base 10x equals negative 51.9 divided by 10. 20, sorry, what did I just say? Divided by 20. Now, how do I solve for x? How do I undo a logarithm? It's 10 because I said log base 10, right? So I would do 10 is equal, so x, sorry. I raise both sides. I take 10 and raise both sides to the power, right? So I would get on the left side x is equal to 10 to the negative 51.9 divided by 20. All right. And if I computed that, I would end up with what? 0.0025. So what does that mean? It means that if my input had an amplitude of 1 amp, my output would have an amplitude of what? 2.5 milliamps. All right. So what it's done is it's filtered that out, it's attenuated. Now, if I look at the top here, so I said it's 60 hertz. The magnitude on this logarithmic scale is 0.00123, which I'm going to say is 0. Okay. What would that be? If I took the magnitude, so if I want to solve for this value here, what would I do? I would say I would divide both sides by 20. And I would say the log base 10 of whatever I'm solving for is equal to 0. What's that thing I'm solving for? 1, right? So what does that mean in the context of what I'm trying to do here? What I'm trying to do is I'm trying to say the magnitude of this thing, right, is equal to 1 at low frequency. It's equal to 0.0025 at the high frequencies. So I'm using this logarithmic thing to be able to express what the actual value is. Because if I looked at the original graph, that original graph is almost impossible to really look at. So we oftentimes put things on the logarithmic scale if there's sort of a really disparate sort of set of ranges that I'm looking at. Like it kind of compresses everything in and lets me see it much, much better. Okay. All right. So this leads us to basically what we're something we call Bode plots, which is a special name for these graphs, right? If I want to draw a graph versus frequency of these things, I make this thing called a Bode plot. All right. So in general, our transfer function is going to be this ugly thing. All right. And it looks like that. And what I want to do is I can figure out how many poles and zeros it has. All right. That's a very complicated looking thing. I don't want to deal with the complicated looking thing. Let's look at a simpler thing. Simplest thing is this guy here. All right. This guy came from my favorite circuit. What was my favorite circuit? It was an RC circuit. Right. So it was basically, and that is, if you ask me what my favorite circuit is, this would by far be it. I have a favorite circuit. That's it. All right. So this would be the transfer function that I would get if I was solving for the voltage across that capacitor. So if I want to make this graph, I plug in S equal to J omega. We said this, we use this terms of poles and zeros. All right. This guy has a pole. I've written that already. It has a single pole. What was a pole again? It's the value of S that makes the denominator equal to 0. So what's the value of S that makes the denominator 0 in this case? What's that? Negative 1,000. Okay. So he's got a pole. Sorry, negative 1,000. Why did I write that one? S equals like that, or negative 1,000. That value of S makes that thing infinite, makes the denominator 0, makes the whole thing infinite. All right. This guy has a single pole. In general, I write this guy like this. Right? I'm going to forget that I have a number here, 0.001, and it's 1 over J omega times 0.001. All right. How do I approach this? Well, what I want to do is I want to figure out how to make that graph. And I want to make that graph on the logarithmic scale. So what I'm going to do is I'm going to take the magnitude of this thing. Okay. So what's the magnitude H of J omega in this case? All right. I want to do it for that general expression, 1 over j omega tau p plus 1. How do I make that? How do I make that? Pandemic times. You guys didn't learn logs. Yeah. How do I get the magnitude of that thing? What do I do? So it's the magnitude of the top divided by the magnitude of the bottom. What's the magnitude of the top? 1. What's the magnitude of the bottom? Square root of 1 over the square root of omega squared tau p squared plus 1. Right? All right, so I want to make the graph of this thing on a log scale. So I'm going to take 20 times the log of both sides. Okay. 20 log base 10 of the magnitude of h of j omega. Okay. So I'm going to take 20 log 10 of 1 over omega squared tau p squared plus 1. All right. So since I know we're not going to remember this, what's the log of a over b? Hey, there we go. All right. Here you go. Here's a 0 point. Maybe half. Right? You do something with it. I wasn't going to do anything with it anyway. There's log 10 of a minus the log 10 of b. All right. So, all right, that's the last one I have. Nobody else can impress me. All right, so log 10 of a minus the log 10 of b. Actually, no. I have a 20 cent euro. So, all right, log 10 of a minus the log 10 of b. All right. So, how do I apply that here? 2 logs, right? 20. Okay. Yeah, 20 log 10. Minus yep. All right. Good. All right. So what's the log base 10 of 1? 0. All right. So I figured out that this thing is negative 20. What the heck do I do with this? What was the point I was trying to make? Well, I want to try to figure out how to make a graph. All right. I'm trying to figure out how to make a graph. So how do I do this? So it turns out I'm gonna make an approximation. So here's what I ended up with. All right, for this single pole, I had this. And if nowadays with a computer, I could just throw that into MATLAB. MATLAB makes the graph for me. But back in the days when men were men, we would go and we would graph this thing, right? So what I'm going to do is I break it up into 2 ranges. What do you think are the 2 ranges I'm going to look at here? So in other words, I'm drawing a graph, just so we remind ourselves, we're drawing a graph versus frequency, right? So what I want to do is I want to look at, how do you think I'm going to define 2 ranges here, 2 ranges of frequency. What do you think they're going to be? What's that? Low and high, right? Low and high. So what would be low and what would be high? Well, I'm going to make an arbitrary thing, and I'm going to say, what would happen if I look at omega much less than 1 over tau p? And then I'm going to look at omega. Okay, so not that you guys are too formal with your math, but what is that greater? What is that? What's greater mean? Extremely greater, much greater, right? Much bigger than, much less than. Okay. So if I have omega much greater than 1 over tau p and omega much less than 1 over tau p, one of those is going to be what I consider low frequency, and the other is going to be what I consider high frequency. Which one's the low frequency? Yeah, much less than, and much greater than is the high frequency. Okay, so these are the low, and these are the high. All right. Now let's think about what happens here. So if omega is much less than 1 over tau p, that means that omega tau p is much, much less than 1. All right, so if I look at what's under that radical sign, I have 1 plus something that's much, much less than 1. So what is that equal to? If I have 1 plus something much, much less than 1, what's that equal to? 1. Okay, so at low frequencies, it says that this guy becomes approximately negative 20 times log 10 of the square root of 1, which I can say is 1. Yeah, what's this become? It becomes 0. Okay. What about at high frequencies? At high frequencies, I have omega tau p much, much greater than 1. So what that says is I have 1 plus a number much, much bigger than 1. What's that equal to? Yeah, I can basically forget the 1, and I can say this is approximately negative 20 log base 10 of omega tau p squared, square root, which would be negative 20 log 10 of omega tau p. Now, what the heck have I done? How's that help? So in this case, I've got log of a times b. All right, what's that guy? Yeah, we're hitting all the greatest hits today, right? This is log 10 of a plus the log 10 of b, right? So that says this guy would become 20, negative 20 log 10 of omega minus 20 log 10 of tau p. All right, what the heck have I just done here? What I want to do is I'm talking about trying to graph this guy on a logarithmic scale. So what I do is it's kind of like on a logarithmic scale, my x-axis, it would be logarithmic. So I can think of this as negative 20x plus a constant. What does that look like? What's just the line? And it's a line that has a slope downward. So what this is saying to me is that for this individual pole here, at low frequencies, the magnitude is 0 decibel. At high frequencies, it's what? It's falling linearly versus as frequency increases on a logarithmic scale. So here's the way that we deal with this. All right, so what I did was I made an approximation. I said for omega much, much less than this value, for omega much, much greater than this value. Omega much, much less than it stays constant, for much, much greater than it falls linearly. What's it do in the middle? We're going to forget about what it does in the middle. All right, and we're just going to say it behaves, it's 0 right up until that point. Omega equal to 1 over tau p, it's 0, and then after that, it falls linearly. If I want to know what it really does, I can go into MATLAB and I'll find out that it doesn't look that much different. All right, my approximation is pretty good. All right, so I want to use this fact to draw this thing. And this is the last thing I want to do today. All right, so I want to use this fact. Now, I'm going to do it for an example. And what I did was I got logarithmic paper. All right, that's what this is. This is a logarithmic paper. And what I want to do is I want to label up the way this graph is going to look. All right. So I got a little table of logarithms here. I said for the number 0.1, 1, 10, 100, and 1,000, I put their logarithms, right? Why is 0.1 negative 1? Because it's the log base 10 of 10 to the minus 1, right? So where are those things? So what I did here was I drew a logarithmic x scale and a 20 logarithmic y scale. So if this is the origin right here, help me out. How do I draw this? How do I label these points? Okay, so the way this works, these graphs are a little confusing, right? These are sort of integer separations here. So this would be 1, 2, 3, 4, like that. And this would be 5. This would be negative 1. All right, you guys follow? Basically, I got the number 0, 1, 2, 3, 4, all evenly spaced because they're all integers. All right, that's on the logarithmic scale. What numbers do they correspond to? What does 5 correspond to in the real omega value? 10 to the 5th. What does 4 correspond to? Oh, 10 to the 4th. What does 3 correspond to? 1,000. 2 corresponds to 100. 1 corresponds to what? 10. This is 1, and this here is 0.1. Now, in addition, what I say is that each of these here is also, right, this is -1, -2, -3, -4, and this would be 1. What do those correspond to? Well, those would basically be, in this case, this would be what I call 20 times that would be 20. 20 times this would be -20. This would be -40, -60, -80. I wrote those in decibels, right? 20 times the log of those values is written down. Okay. Now, what I have here is the h of j omega is this 1 over j omega times 0.001 plus 1. Okay. So what we just did on the previous slide is we said, all right, I want to graph 20 times the magnitude of this thing. In other words, I want to graph 20 times the magnitude of this guy. I look at this at low frequencies and I look at this at high frequencies. What was our definition of low frequencies? Omega much, much less than 1 over tau p. What is that here? Omega much, much less than what? Yeah, 1 over 0.001. So omega much, much less than 1,000. And omega much, much greater than 1,000. At low frequencies, I said this guy is approximately what? 0. Okay. At high frequencies, he's what? He's basically falling linearly. All right. And what's his slope? -20. So here's how I'm going to do this. I'm going to say right up until the pole, he's flat. I should have multiple colors here. Okay, so I'm going to try. All right, right up until the pole. Where is the pole? Right up. So be careful. Where's the dividing line? Let me call it this way. Where's the dividing line between low and high? 1,000. So right up to 1,000, I'm going to say he's flat. Then beyond that, what am I going to do? Draw a line going down. And what's his slope? -20. So basically, this guy, so when I get to 10 to the 4th, where's he going to be? He's going to be at -20, right? So he's going to fall like that, right? That is what I call the Bode plot, right? That is the name of the plot that we make for this thing. All right, this guy is, we sometimes say this slope is -20 dB per decade, right? Because I said I gave this definition, basically a factor of 10 of frequency was what I call the decade. So I say this guy falls at -20 dB per decade. Who's Bode? Bode is the guy that made the plot the first time, right? So we call these things Bode plots. They're really useful for designing filters, for designing these types of circuits. All right. So all right, how do I use this stupid thing? All right. Let's say my input to that circuit was cosine 10t plus cosine 100,000t. And I asked you, all right, tell me the output voltage. What's the output voltage going to look like? It's going to have 2 sine waves in it. One's going to have a frequency of 10 radians per second. The other one's going to have a frequency of 100,000 radians per second. What is the amplitude at 10 radians per second of the output? So where's 10 radians per second on the graph? 1, right here. So at that point, the value 20, so I say 20 log 10 of the magnitude of h of 10, h of j10, is equal to 0. Okay. So if I undo, how would I figure out the actual magnitude at that point? I divide by 20, raise both sides to the power of 10, right? So what would that end up being? Be 1. If I did, so the other one, I say 20 log 10 magnitude h of j 100,000. What's that equal? Let's take a look. Yeah, so if it's falling off at 20 dB per decade, all right, it turns out it would be right here. So how many dB would that be? -40, right? So this guy's equal to -40. So what I do is I divide both sides by 20. So I have log base 10 of the magnitude of h of j 10 to the 5th is equal to what? What's -40 divided by -20, or -40 divided by 20? Yes, -2. So what's the magnitude at that point? Yeah. 10 to the -2, or 0.01. So what would be the amplitude of the output at 10 radians per second? The amplitude of the output would be 1, right? What would be the amplitude of the output at this frequency? 0, yeah, 0.01, right? So what I'd see is I've a really big signal at 100,000 in the input, but a really small one in the output, right? So it's filtered that away. Now it's also doing stuff to the phase. I'm just ignoring the phase. I'm only looking at the magnitude. You guys want me to do that, right? You don't want me to start doing other stuff, right? This is going to boggle your head a little bit. All right, what happens with this inevitably for everybody in this class, or what I always find is when I first show this, you're like, what the heck is he's taking logs and square roots and there's all sorts of stuff going on. But after you kind of learn it, it's a very easy set of graphs to make, right? What I just showed here was that if I had this pole for frequencies lower than the pole, this guy was flat. Frequencies higher than the pole, he falls. If I looked at a 0, how would it be any different for a 0? Well, a 0 would have the same form on the top. He would basically be flat below the 0, and then he would rise above the 0. And the nice thing is, if I take the log, if I had this crazy ass looking thing here, right? And I take the log of it, what happens to the log of a product like that? You add them all, right? So it turns out if you know how to deal with one pole and one 0, then you just add everything up. And that becomes a really easy graph to make. So everybody gets like, wow, this is crazy, the logs, there's all sorts of stuff. But actually, it simplifies itself quite a bit, all right? In general, this is usually one of the things people do the best in once they realize that it's fairly straightforward. Just looks ugly at first, all right? All right, so we'll have more examples of that next week. And I guess